This video is going to be about conformations, and what this really means is the ways in which molecules will be arranged in space. So that's one way you can imagine a butane existing. You can rotate around single bonds, so here's another form of butane. And of course, the way we tend to see butane drawn on the board is this conformation, which I will refer to as staggered, or maybe zigzag, where the carbon chain is always going up and down like that. So why do we always draw it this way? Well, I hope that I've convinced you already that organic chemists will always choose to draw things the way they do because they're trying to show a specific depiction of reality. That really the reason why we draw things the way we do is because that's the way it looks. So there must be a reason then why this molecule chooses to line up in a certain way. And what is that reason? Well, it always comes back to energy. So let's simplify this down to the smallest, simplest possible case, and that is an ethane molecule. So here's an ethane molecule. I've got a green ball on one hydrogen just to make it easy to see what I'm going to do, and a red ball for another hydrogen. If I turn it so that the red ball is facing you, this is what we would call an eclipsed conformation, and I'll show you how to draw these shortly. But what you're looking at is you're looking down the carbon-carbon bond of ethane with the red in the front and the green in the back, and you can see that all the bonds are lined up. This is called an eclipsed conformation. A staggered conformation is instead something more like that, where you can see that the red ball is not any longer aligned with the green ball. As it turns out, this is going to be much easier to show you in ChemDraw sort of settings, so I'll shift to that shortly. But first, let me show you how we go ahead and draw a molecule like this with what we call a Newman projection. Again, the idea is always going to be that we are looking down a carbon-carbon bond. What you're looking at on the board are classic Newman projections drawn for ethane. So on the left, you have the staggered, which is the lower energy conformation. What you're looking at is a depiction of the molecule where the carbon containing the red hydrogen is in front and the carbon containing the green hydrogen is in back. The Newman projection shows that the atom in the back is depicted by the circle and the atom in the front is depicted by the Y. The staggered conformation, which is the one on the left and the one that I'm holding, is the lowest energy conformation with the least amount of strain. If, however, you rotate the molecule such that the red hydrogen and the green hydrogen are aligned, then you have what is called the eclipsed conformation, and that is much higher in energy. Broadly speaking, the right way to think about it is every HH eclipsed interaction, like the red H and the green H eclipsing, is worth about 1 kcal per mole, so 1 kilocalorie per mole. So this eclipsed interaction is about 3 kcals per mole higher than the staggered, because there are 3 different single H's eclipsed in this conformation. So the way I'm going to be showing you these Newman projections is going to be with the red group in front in all cases and the blue group in back. So we're looking down the red carbon atom to the blue carbon atom in all cases. Then the methyl that contains the red hydrogen is attached to the red carbon atom, and the blue carbon atom has the methyl with the green. So this is the angle that you're looking at in the Newman projection to the left. Red in front, methyl with the red attached, and so on. This is the best possible case where none of the atoms are aligned. None of the hydrogen atoms are aligned with the hydrogen atoms in the back. This is fully staggered. And moreover, the 2 largest groups, the 2 methyls, are anti to each other. This is the best case scenario. This is 0 energy as far as we are concerned. If you rotate the group that is in the back and hold this group constant, the next staggered conformation looks something like this. This relationship between where the 2 methyls are is referred to as gauche. So we have a gauche methyl arrangement here, although everything else is staggered. So this is 0.9 kcals per mole higher than the Newman projection we were just looking at. If I rotate a little bit further and I arrive at something like this, now absolutely everything we have is eclipsed. Specifically, this is the worst possible interaction where the 2 methyls can just about, but not quite, bump into each other, but the 2 methyls are eclipsed and the hydrogens of the red are eclipsing the hydrogens of the blue. This is the worst conformation of all, and this is worse by about 4.5 kilocalories per mole over the best possible staggered conformation, which again is the Newman projection on the left. As far as the energies that are involved, hydrogens eclipsing other hydrogens is about 1 kcal per mole. So in the ethane case, the worst eclipsed one is 3 kcals per mole higher, 3 different HH interactions. Methyl eclipsing a hydrogen, for example, this methyl eclipsing this hydrogen in the back, that's worth about 1.3 kcal kcals per mole, and a gauche methyl interaction, which is to say the methyl in the back at this angle relative to the methyl in front, or alternatively that way, those gauche methyl interactions are about 0.9 kcals per mole. And then having the two methyls eclipsed is about 2.5 kcals per mole. So the reason why this is 4.5 kcals per mole higher is 1, methyl-methyl eclipsed interaction, and 2, HH eclipsing interactions, which brings the total energy up to 4.5 kcals per mole.
To put this in context of what the book has, it will have descriptions like this, where it shows you the eclipse conformation and the staggered conformation, balls and stick models, or perhaps line angle structures. And what I've just been describing to you is Newman projections, with again, the Y is the front carbon and the circle is represented by the back carbon. And the dihedral angle defined by the 4 atoms, this hydrogen in the back, the circle, the Y, and this hydrogen in the front, those are what we will vary as we rotate things around each other. The book shows that eclipsed interactions are less stable than the staggered conformations as I've described. And again, the rule of thumb is that a hydrogen-hydrogen eclipsing interaction is worth about 1 kcal per mole, so that this is roughly 2.9 kcals per mole more stable than the eclipsed interaction. You can imagine creating an energy diagram as you hold the hydrogen in back constant and you rotate the hydrogen in front around. And that's what's happening in this diagram. This hydrogen is staying constant, the one that's in the back, and all we're doing is rotating around the one that's in the front. And you go through alternating staggered and eclipsed conformation. And in every case, the eclipsed conformation is about 3 kcals per mole higher, and then we go back down to a minimum, and so on and so forth. If we're going to be a little bit more precise about the energies, then we can use our drawing program Gaussian and do a plot of the energies as we scan around the various possibilities. So what I'm going to do is simply rotate the molecule slightly. The problem is every time I click on the next possible iteration, this molecule may rotate on us. So if we look at what one of these energies is, it's very clearly an eclipsed interaction where everything is lined up. And if I look at the next one, there's really no difference once I line it up again. You can't tell the difference because all hydrogen atoms are the same. So every single one of these high energy points is going to be your eclipsed interaction. Obviously, if you're not perfectly eclipsed, but you're at some intermediate value, then you'll find that we're approaching being eclipsed or approaching being staggered, but we're really not quite either. Then, of course, your lowest energy states are going to be your staggered conformations. Here, what we're going to do is look at 1,2-difluoroethane, and what I'm going to do is to rotate through, and we're going to watch the energies as we move around. At the moment, of course, we are in the global minimum for energy, the lowest possible energy, where the two fluorines are directly opposite each other. They are anti to each other, and this is a staggered conformation. So what I'm going to do is rotate around, and you'll find that the next interesting place that we arrive at is going to be a maximum. And so every 60 degrees or so of rotation, we end up in an interesting conformation, whether it be staggered or eclipsed. Every time we have an eclipsed conformation, we are at a maximum of energy, and the global maximum of energy will be when both fluorines are lined up with each other, eclipsing. But here we are at a local maximum. If we rotate through another 60 degrees, we will arrive at another staggered conformation, and now what we have is the two fluorines are gauche to each other, and because the two fluorines are gauche, then we are not at a global minimum, we are instead at a local minimum. We're going to continue around and arrive at the global maximum. And the global maximum takes place when both fluorines are eclipsed. So now we have the two fluorines eclipsed, and the other hydrogens are all eclipsed as well. This is always the highest energy, and then we can continue rotating until we arrive at the next local minimum. And again, what we have here is essentially the two fluorines are gauche, and then we continue on around until we arrive at another eclipsing interaction, and then we continue around until we arrive where we started. I mainly did the difluoro case because it allows you to see more clearly as we maneuver through the various points. And once again, there's always going to be 3 maxima, and one will almost certainly be the global maximum. And we're going to have 3 minima. The 3 minima are always going to be staggered, and the 3 maxima are always going to be eclipsed. Here we're going to look at propane. And the interesting thing about propane, of course, is that since we have a single methyl group, there will be no gauche methyls possible. So in our case, the 3 maxima will all be identical, practically, and the 3 minima will all be identical. You're either eclipsed or staggered. We alternate between conformations where everything is eclipsed, and the only thing that changes is which specific methyl is lined up. You notice as I click between the various energies here, there's no change in the picture. And likewise, if I go to the global minimum, everything is staggered, and if I change among the minima, there's no change in the picture. Of course, the only difference between propane on top and ethane down at the bottom is how much energy is involved. In the propane case, we have at the global maxima 2 eclipsing hydrogen interactions, each of which is 1 kcal per mole, and then a methyl eclipsed with a hydrogen, which is about 1.3 kcal per mole. Likewise, with the ethane situation, everything will be eclipsed, but all 3 of the interactions are CHs, so this is 3 kcals per mole higher. So this is 3 kcals per mole higher at the maximum than it is at the minimum, and in propane it's really about 3.3 kcals per mole, not significantly different. And now we're going to examine a butane conformational analysis, and here we have butane again at the global minimum where the methyls are anti to each other at the very bottom energy, and these local maxima are first where the methyls are aligned with hydrogens, but then we arrive at the global maxima where the methyls are aligned with each other. Those methyls being aligned with each other is 2.5 kcals per mole, and the 2 hydrogens are each 1 kcal per mole, so where we end up is 4.5 kcals per mole higher at the global maximum than at the global minima. Meanwhile, what's different at these local minima is that we always have a Gauche interaction, where we have the methyls essentially 60 degrees away from the methyl that's in the back, and that's really the situation that we have in both cases. So the local minima are the Gauche methyls, the global maximum is the methyls eclipsing each other, and the local maxima that aren't global, we have the methyl eclipsed with a hydrogen in at least 2 cases. And that's butane. Perhaps you prefer some of the illustrations that are in your book as opposed to what I was just showing you. Here is a propane that is eclipsing where we have the methyl aligned with an H, and that's worth 1.3 kcals per mole. Again, with 2 H's eclipsed, these H's are eclipsing both sets, and that's 2 kcals per mole, and that's 3.3 kcals per mole. Ethane has 3 kcals per mole as the highest energy interaction. With butane, there's an enormous difference in energy, relatively speaking, between the most stable version, where everything is staggered entirely, and the 2 methyls are opposing each other, anti to each other. Whereas when you have a staggered conformation and the 2 methyls are 60 degrees from one another, then you have what we call a Gauche interaction. The book is claiming that this is 0.8 kcals per mole, and I mentally have logged it away as about 0.9 kcals per mole. The point is, it's a little bit less than a standard HH eclipsing interaction, but it's around 1 kcal, give or take. Finally, the really bad interaction for butane is everything eclipsed, and in particular, it's the 2 methyls eclipsing that's worth about 2.5 kcals per mole, because we know that the 2 hydrogens eclipsing are worth 1 kcal per mole each. So 2 kcals per mole for the hydrogens, 2.5 for the methyls, 4.5 overall. When you have this situation where the 2 methyls are eclipsing with hydrogens, each of those is worth about 1.3, so that would be 2.6 there, and then the 2 hydrogens interacting is about 1 kcal per mole. I am not entirely sure why the rounding in the book gives it as a 3.7 kcal per mole when the rough rule of thumb would give you 3.6. Point is, it's pretty high, but nowhere near as high as the 4.5 kcal per mole interaction. And then the main reason to show you this particular image is to just show you what the Newman projections look like for all of those images. I was showing you what the actual models look like. Here's how you do the Newman projection. Again, notice that the Y is always the atom that's in front. So here, the methyl in red is closer to us than the methyl in green. But other than that, all we're doing is rotating around while holding the methyl in green in the back constant. And we pass through what is the best possible conformation at 180 degrees. And the worst possible conformation is where we started and where we finish. And Gauche is going to be good, but not as good as anti. And these interactions are going to be bad, but not as bad as the 2 methyls overlapping. There's really one last point to be made here with the conformational analysis of straight chain molecule like butane, and that is that you might think that the source of the bad interactions is the actual hydrogens rubbing together, which is to say that maybe these hydrogens are actually touching each other. But when you look at space-filling models, that's not actually happening. These hydrogens really can't get close enough to each other to actually contact each other. So what is the source of this high energy? What is the source of this bad conformational energy? Essentially, it has to do with electron pair repulsions more than anything else. We call it, generally speaking, torsional strain. But really, what it has to be more than anything else is either bad interactions between electron pairs, but that's not necessarily a convincing answer because these hydrogens are fairly far away from each other, not necessarily touching. So that means that the electrons contained with the carbon-hydrogen bond probably aren't that close to each other and aren't really repelling each other all that much. No, in fact, what's probably going on is something quite quite a bit more complicated. That is donation of electron density from a full CH bond into a sigma star orbital on the backside of another carbon. That's a strange thought, but I'm going to illustrate it for you on the board.
So the idea is simple, if a little bit weird. Here I've drawn ethane, and I've drawn out the ethane from the side so that you can see the sp3 hybridized carbon center. The hydrogen, one is coming toward you, one's going back away. This one's coming toward us, one's going back away. This is ethane in a staggered conformation, and so it should be low energy, relatively low strain. So there's two ways of thinking about it. One is that these things would be repelled if they were eclipsed, but that's not really what's going on. Instead, what you want to think about is the sigma orbitals in this molecule, and both of these blue orbitals that I've drawn are sigma CH orbitals. There's a carbon sp3 making a bond with a hydrogen 1s, and that creates a large lobe where more of the electron density is between the carbon and hydrogen itself, and a small lobe back there. There's no interaction whatsoever between the sigma in both cases. However, anytime you create a sigma, you are also creating a CH sigma star. And the lobe here is largely going to be behind this carbon atom and out beyond this hydrogen atom. And really, there's not much electron density in the middle. There's a lobe that's on both sides of this carbon atom and a node running right down the middle. And again, another node that's directly between the carbon and the hydrogen. So anyhow, where the electron density is for this sigma star orbital, where it would like to have electron density anyway, is right back there. And notice now that this full sigma orbital that has 2 electrons in it is pretty well aligned and relatively close in space to the CH sigma star, and so it can donate some of that electron density right there. It's a little bit of a stabilizing interaction. And you might ask yourself, well, hold on, if you're partially filling this antibonding orbital, wouldn't that tend to lengthen this bond? And yes, it's true, but you get a little bit more out of this positive interaction than you lose on the negative interaction on this side. Am I making this up, or is there really evidence for this? Well, actually, this is very, very similar in concept to the picture that we draw a little bit later in the semester when we're trying to describe why it is that cations have the stability that they do. Ethyl cation is a relatively bad cation. Tert butyl cation is a much, 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 much better cation. And the reason why this is true, at least in part we believe, is due to the ability of nearby CH bonds, like this one, to donate electron density into that empty p orbital. The explanation that we have for why ethyl is a relatively bad cation and why T-butyl is a much better one is in this molecule we have 9 hydrogens that can all potentially donate into the empty p orbital. 3 at any one time, but still that's a lot of hydrogens that can donate in, whereas in ethyl we really don't have that many. There's really only 1 at any one time that's lined the right way. So we know, in the case of cation stability, that this is a really important factor. This donation of electron density from a filled orbital into an empty orbital, called hyperconjugation, is a really important concept when it comes to cation stability. So it stands to reason that this is the source of the conformational analysis that we've just discussed, that there's a little bit of electron density donation from the sigma orbital into the sigma star, and that really the staggered conformation is lower in energy relative to the eclipsed conformation, which is relatively higher in energy. Your mileage may vary. Certainly, intellectually, it makes sense for you to think of the hydrogens as essentially repelling each other when they're eclipsed. It's just that in reality, they're probably too far apart to actually do that. In reality, probably what's going on is this through-space interaction is lowering the energy of the staggered conformation. So conformational analysis of acyclic molecules really comes down to trying to always be in the staggered conformation, trying to always avoid the eclipsed conformation.
And again, here's the point. If we're just looking at these 2 carbon atoms and the hydrogens associated with it, this hydrogen is more likely to be able to donate electron density into the sigma star orbital that's hanging out right here, the carbon-carbon sigma star orbital that's right there, than this hydrogen is to bump into other hydrogens which are nearby and relatively small. But it doesn't really matter if this is a positive interaction lowering the energy of one or a negative interaction raising the energy of the other. What we know is that eclipsed is worse by about 1 kcal per mole. And though we're not entirely sure which explanation is better, my money is on the through-space bonding interaction of the sigma, full sigma, with the empty sigma star as being a better positive interaction, lowering the energy of the staggered conformation. That's the way I would tend to bet.